Thank you very much. As Chris said, I'm Milo Barham, and today I'm going to be talking about heavy minerals, some new advances in that space. But of course, this isn't only my work. I've got to recognise that this is the collective work of a number of different people, particularly within the timescales mineral systems group that we've had over the years. We've been very lucky to have some exceptional PhD students and now postdocs working in this space with us. So why do we actually care about heavy minerals? Well, I obviously do care about heavy minerals, and I'm trying to convince you that you should as well. Well, heavy minerals, obviously we're talking about a range of different minerals here, and they can represent important archives of different crustal processes, whether that be the pressure, temperature, fluid migration, etc. And this is all captured via kind of isotopic chronometers or different trace elements, or even within their textures of those minerals. And some of those mineral phases that are particularly robust and resistant to some of these geological processes of overprinting or even the weathering and erosion processes, they can preserve a record of those geological processes through deep time. So as detritus, so the original rock record may be destroyed, but the record of those events could be preserved within the sedimentary record. So the sedimentary record via these detrital heavy minerals can actually be a more complete geological history of our planet. And obviously that's evidenced quite nicely by the Jack Hill zircon being the oldest preserved piece of our planet itself. We can also look at detrital minerals for tracking surface environmental processes. So some of those heavy minerals that maybe are impacted by the weathering and erosion features, they can actually inform about the environmental processes they've been exposed to, so therefore capturing something about modern environmental processes or ancient environmental processes in the past. In some ways, nature does a lot of work for us by gathering geological information for a wide area and maybe concentrating them down into a particular sample site for us. So they could be capturing a kind of integrated history of a larger region's environmental history, as well as local environmental histories, and the same for the crust history that it represents. HM also can act as pathfinders, so specific heavy minerals or specific isotopic ratios within those heavy minerals can be diagnostic of particular mineralization processes. So although the ore deposit itself may be buried undercover, which is obviously quite common within Australia, they can be weathered into the overburden and maybe transported into a larger halo, so the kind of secondary footprint of these ore systems can actually be more easily targeted in exploration than the actual direct ore deposit body itself. So they can be very useful as pathfinders, larger exploration target, but also heavy minerals in their own right are economic. So we can think of a number of different minerals, and we'll go a little bit deeper into that now, looking at Australia's mineral wealth. Obviously, Australia is number one in the world for a number of different heavy mineral phases, things like zircon, rutile, ilmenite, and also a significant producer in other areas such as rare earths that may be bound in some of the heavy mineral phases like monazite, maybe xenocene, things like that. So we're also number one in garnet, maybe less of a celebrated heavy mineral for its economic importance, but also these industrial minerals are important. So we're talking about very, very significant kind of representation of heavy minerals coming from Australia. So 50% global production, particularly in garnet. And this all links back to the geology of Australia itself. So we have these ancient kind of cratonic areas, but also that have been modified through time, kind of at these kind of plate boundaries where we have these dynamic geological processes that enhance the mineral fertility, but we also then have this extensive history of basin development and then opportunities for reworking of those sedimentary systems to upgrade some of these different more resistant mineral phases. It's things like zircon and rutile have demonstrated, as we'll see for the rest of the talk, extensive multi-cycle histories that are kind of part of the character, part of the story of why Australia is so rich in some of these heavy mineral economic resources. And these economic resources, these heavy minerals, they go into such a wide array of different things that we experience every day. So things like zircon, rutile, ilmenite, these are going into glazes and ceramics. They're going into the titanium into surgical implants, into aerospace, they're going into sunscreens, then we have rare earth elements that may be going into magnets, that are also going into the green energy transition. We have zircon going into casting and foundry. Anything that you have that is white, there's pigment and paint, then you are probably looking at some kind of titanium dioxide. It's even allowed in food products in Australia. So what exactly are we talking about when we're talking about heavy minerals? Any mineral that is particularly dense, over 2.9 grams per cubic centimeters, and these can be of diverse composition. And these images here are just kind of showing you the impact of those different densities have on the way that those minerals are transported. So these, basically the more dense grains can be smaller than a less dense grain, but they'll be, because of that mass difference, they can be transported in the same sort of energy system within a sedimentary environment. So the mass impacts the transport of those grains, and this is part of the reason why they start getting fractionated in these sedimentary systems to concentrate the different minerals into different areas. Because we're always looking at these kind of balances of forces during the transportation of those grains. And what can then lead to the concentration of them, or the modification of them to different degrees as well, because obviously these different minerals have varying kind of reactivity with different fluids, whether they're groundwater, whether they have different cleavages, with different hardnesses. All of those impact their survivability within a sedimentary system, and also when they're in diagenesis, shallow burial, or low metamorphic conditions as well. So today I'm going to cover a few different areas of kind of new advances in heavy minerals. We're going to look at some different minerals that people are starting to work on now, new tools that we're applying to minerals, and how we're integrating across different tools or different minerals to get a more holistic view of things. We're going to look at some of the improvements in accuracy, speed, and reproducibility of data, and what we can start doing with some of these big data and the big pictures we can create with them. So overall, that is getting that more holistic kind of interpretations. And these have obviously academic interests, but they're also fundamental to the mineral systems and the economic resources that society depends on. So the reason why we want to look at new minerals and tools and integrations is that obviously these different isotopic systems within different minerals have different closure temperatures, or maybe they're different sensitivities to different geological processes. So by using these different minerals or different isotopic systems, we can span more of a complete kind of range of different geological processes we may be interested in understanding, and in the past basically getting a more complete history of the thermal history of a rock, or maybe the different phases of fluid passing through a rock. We can track that using the right tool for the right job. So we've got a number of different advances that have gone on in analytical techniques that have opened up the possibility of analysing new minerals, or maybe increasing the rate at which we could analyse those minerals, that then has made it a reasonable tool to use. So we'll cover some of these, like garnet, but also things like rutile, coltan, bdelliite, cassiterite have all started coming on into more common usage. So we're looking for that Swiss Army knife, basically to capture that geological history, whether that be different survivorship biases, different reactivities to different events, different closure temperatures, or different parts of the crustal history. And by integrating them together, we get a more refined geological interpretation. So we're very lucky here at the Curtin Frontier Institute of Geoscience Solutions that we're blessed with world-class facilities and the expertise to kind of value add to those facilities. So we have a kind of reasonably standard workflow in terms of sample preparation, characterization, the in situ analyses that's possible, and then what we can take from it. And we'll work through some of that now. So as the first kind of example, we talk about garnet, and obviously garnet has been used in this case, I'm going to talk about it in provenance setting, has been used in detrital studies for decades, and initially it's just a simple presence in terms of saying something about the source region that's supplying it, but also then looking at ratios, and in more recent times we're looking at machine learning of grain chemistry, so getting quite advanced. And what's happened with some of these techniques obviously is that there's a lack of unique signatures, so presence alone isn't going to be really able to resolve the detail you may require, or there's complexity of the approach or low sample throughput that's not going to get a representative kind of sample for you. In the last few years, there's kind of been improvements in understanding of the reaction cell or collision cell capabilities integrated into a laser ablation ICP-MS system, so that we can start taking out mass interferences and be able to resolve aspects of parent-daughter relationships to, basically in the case of garnet, enable in situ lutetium hafnium geochronology directly into the garnet. And this has generated these diagrams that I should probably explain, where we're going to look at this inverse isochron space. So at time 0 we have maybe a range of different compositions of or concentrations of a parent isotope that will decay, and then if we look through time, where we had a higher amount of let's go to pointer and laser, where we had a higher amount of the parent, that's going to then generate a larger amount of the daughter. So through time you'll get these arrays. If it's a single kind of event, a single time, you'll get these arrays that steepen over time. So in this diagram in the bottom right, you can see that there's two different populations, a younger rim and an older core age. So we can use these to date garnet in situ. So with that, we'll look at a beach situation here in Western Australia, where we have these beautiful pink or purple garnet beach sands. So we undertook a few different samples along Western Australia, 3 different samples from down near the Capes region, then around in the bay above that, and then up closer to the Northampton complex. So looking at the Yallingup down around the Capes region first, you can see that we have 2 different sessions here, the green and red, very useful for colourblind people, apologies, that basically show there's a single population and very stable between these different analytical sessions, and we have an age of about 550 million years. We look at Port Gregory in the north, near the Northampton complex, and it looks quite distinct. We've changed the scale slightly, but this is coming in with an intercept age of just over 1.1 billion. So 2 distinct populations, it seems. Now if we look at the Milo sample in between, we get something a little bit more complex. Here I'm not showing the green and red different analytical populations, but what I'll do is I'm going to start pulling these out into 2 different populations, I think, and here we have the green and red showing 2 different analytical sessions. Here it looks like there's a greater spread of data, and I would argue there's 2 populations here, and this is supported by grain chemistry, specifically calcium. The younger population seems to be coming in, so this would be the less deep one, this seems to be coming in around 580. And then there seems to be an older age population as well, just over 1.1. And these match very nicely within uncertainty what we'd seen previously in terms of the 550 population at Yallingup and the just over 1.1 up at Port Gregory. So it seems like we're getting a combination of the 2 populations evidence here at Milo. So if we then integrate that with the ages of the zircon, uranium, lead geochronology that we took from the exact same sand samples on the modern beach, you can see that the red, the garnet age, and the grey, the zircon ages, show some similarities, but that they're slightly offset, with the garnet slightly preceding corresponding zircon age. This is demonstrating the robustness of this lutetium hafnium geochronology and the, I guess, slightly different age kind of record it's picking up of that specific crustal event that is generating these mineral phases. So what can we say about this? We can recognize that the grey, these detrital zircon age signatures, are showing a much greater catchment, much more kind of mixed and reworked polymodal age signature, whereas the garnet seems to be much more unimodal and picking up much more of the kind of local basement. We've got that correlation but subtle offset, demonstrating the primary signal retention in the garnet that is with this lutetium hafnium method. And we've got this support in these samples suggesting that we have continuity of basement beneath the Perth Basin, connecting the Northampton complex and the Lewin complex. And this is something that came up recently in some basement drilling they've done through the Perth Basin, and seeing that continuity of those age signatures. So we're not just looking at very distinct kind of Lewin complex versus Northampton complex, but there is a continuity of age signatures and similarity beneath the Perth Basin connecting these systems. So you can see how the integration of these geochronometers can work quite nicely and further enhance the kind of understanding of a region through the integration of those techniques. We can also look at other mineral kind of mergings. So we can look at, because of the different fertilities or the mineral and isotopic survivorship, we could look at, say, apatite and zircon. Apatite maybe being able to pick up mafic contributions, so source regions that are more mafic, that zircon may be blind to, but also apatite being much more sensitive to some of the kind of exposure to acidic meteoric fluids, and so they tend to disappear during weathering and erosion. But we can look at that different survivorship to understand maybe the degrees of sediment reworking or source region contributions. As Anthony Clark did is some of his work up in the Pilbara, looking at the unroofing of the Pilbara domes through the integration of the zircon and the apatite. And equally, we can use those same techniques in a completely different setting. In this case, looking at archaeological sites and the kind of human transported artifacts and where they may have come from. So analysing detrital minerals in some of the altar stone from Stonehenge, and trying to match that with unique source region fingerprints of where it may have come from. So in this case, suggesting a kind of Orcadian Basin origin, so in Scotland for some of the material, the altar stone in this case for Stonehenge. Integrating apatite and zircon also works in other settings. In this instance, Jack, PhD student here, looked at apatite and zircon and other accessory mineral phases within salt, with the idea that salt bodies are proposed as being significant for potential underground storage of green hydrogen in the future. So we have these potential for large underground caverns in these salt bodies that could store huge quantities of hydrogen. But the issue being with salt that the salt bodies are mobile. They are typically very poorly constrained temporally because they don't have directly datable phases, or they don't have maybe biostratigraphic age control within the salt themselves. But by looking at some of these accessory minerals contained within it, maybe we can better constrain the maximum depositional age, or maybe they have a greater kind of chance of concentrating volcanic inputs into these basins that otherwise were getting reduced clastic input. So looking at these integration of the apatite and zircon, it was possible to suggest a new age, because we have this similarity of these youngest zircon and youngest apatites, and these apatites have distinct shape characters that suggest they have not been extensively transported. That enabled us to suggest a young age suggest an age for this salt body, which actually was suggesting there was an older salt body that had pushed up through the sequence, and it was a diapiric salt body, in this case from the Canning Basin, from rock salt. And this can also be used, apatite zircon, integrated again, this time in a Precambrian sequence to understand stratigraphy of a mineralized sedimentary sequence, to try and demonstrate where sediments were recycled versus where there was first cycle sediment generation. So in the top here we have good agreement between the apatite and zircon, suggesting this is first cycle and relatively proximal sediment generation, whereas here on the bottom we see quite a disconnect between the zircon and the apatite, suggesting that these older zircon ages with very poor apatite representation, this is a population that has been extensively reworked and has basically destroyed the coeval apatite, whereas this is demonstrating that this age signature here is much more first cycle and local, but the zircon relative zircon contributions at this age is very low because it's swamped out by this large recycled component, and in this case this is from Tasmania, and originally coming through multiple phases of recycling from North America as its ultimate source. Not just zircon and apatite, rutile also offers great opportunities, and we can look at kind of multiple different kind of signatures or proxies within an individual mineral phase, and that can be done with zircon using split stream analyses, or it can be done with apatite or with rutile, where we can look at both a uranium-lead geochronometer, for instance, on the left, which may not show so much variation and looks quite kind of similar, but then we can also look at the chemistry within it that might suggest something about the source region composition, whether it's the chromium and niobium, looking at palitic and mafic source regions, or we could look at zirconium and rutile as a thermometer to say what temperature they were forming at, or we could look at uranium thorium helium ages to say maybe when they were exposed to a later thermal event, or when they were maybe brought to the surface from depth. So using those integrations of those different signatures, you can get a much more resolved picture of the history of those grains. And in this case, because we have these different thermal windows we're passing the grains through, we were able to, from samples from southeastern Australia, demonstrate that a lot of the rutile was actually coming from central Australia via intermediate basins and reworking. So we have this extensive production of rutile in the central Australia and being distributed quite widely across Australia through the intervening hundreds of millions of years. And the reason why these are all important is because these geological processes underpin mineral systems. So the source region composition and magmatic history is all about the fertility of those regions. But being able to track things about where the grains have come from, their routing, any sort of intermediate burials and any sort of reworking, that overall source to sink history and that modification and maturation of the cargo, that is all going to be about the upgrading of that cargo, and that's all going to be happening during the transportation and the trapping phase. And if we can try and get some absolute age constraints on sediments, or better age constraints, then that's going to be important for the timing of these different events to put together this classic kind of mineral system history. And that has always been a bit of an issue, is that middle phase of, we may be quite good at getting where the source is, and we might obviously understand where it is now, but that transport history, that intermediate history of the sediments from that source to sink was in the past quite cryptic. But we understand from modern systems that it's hugely complex, and that is really diagnostic of the ultimate. It has a huge impact on the ultimate sediment that you're producing. So some of the kind of new metrics we've developed to try and understand some of that intermediate history. This is one developed in this case to help understand the potentially infer something about the tectonic history that the sediment was deposited in, or the catchment complexity that the sediment was deposited in. So in this case, we've looked at this example is from obviously South America, and we looked at the kind of variability of the age signature. So we have an age spectrum, and we looked at how variable that was, how complex it is. And obviously if it's coming from a single source, then it's going to have a single age peak, whereas if it's starting to mix multiple different sources and multiple different ages, we're going to get more polymodal and increasing polymodal samples. And the blue colors here are basically capturing some of these metrics, looking at this chi-squared metric to understand, and also looking at basically how concentrated the young ages are compared to the overall age spectrum. So the increasingly darker blues are saying something like this: it's most likely coming from passive margin, whereas the reds are suggesting it's coming from a more active margin. So you can see this quite nicely tracks the progressive change down along the river as we're mixing more and more different ages into it. So we can use these metrics to track actual geological processes in the modern as well as the ancient past. Another metric we can start looking at to understand the mixing and reworking of sediments is something like a source normalized alpha dose. So obviously there's radioactive elements in a mineral, and they break down And as they are breaking down, these radioactive decay actually can damage the crystal lattice. So we can start kind of calculating how many different radioactive events, I guess, within the crystal, and therefore what sort of inference we could suggest about, just pure based on the uranium concentrations, the age of the sample, we can make an inference about how much damage that mineral has accumulated. And the idea is that a more damaged crystal lattice is more susceptible to being destroyed during transportation and reworking. So if we take a sediment that's sitting directly on top of its source region, its alpha dose recorded in the grains should match that of the crystalline bedrock it's sitting on. Whereas if we then transported it further and further, we may see that the grains with the higher alpha dose are being more progressively destroyed. So the ones that had a high uranium concentration or are older, they'll be more likely destroyed than some of the ones with a lower alpha dose. So we can compare the alpha dose of a population to try and normalize it, to track it through its progressively through different kind of intermediates to see how matured or how reworked is it from its original source. And we can track that in places like the Albany-Fraser origin, going from these different systems into modern sediments from older sedimentary basins. You can see that progressive drop. You can track it through the Grenville in North America, through these different inferred sedimentary systems that the grains were being reworked from older into younger. And you can see that progressive down. Whereas if we look at a modern sediment sitting on top of its crystalline source, you can see that it's sitting at the 1, basically it's the exact same. So this works nicely along through one sedimentary unit into another, or one basin into another, but also tracks with modern kind of environmental processes like longshore drift, where we'll see the different source regions quite nicely here from material that matches the age of the Pinjarra origin, progressively getting lower and lower values along transect along the coast, showing the longshore drift impact. Other kind of tools that have recently been developed for that cryptic heavy mineral history is something called cosmogenic krypton. So we have these cosmic rays, which are high energy particles generated from supernovae or from our sun, but basically out in the universe we're generating these cosmic rays that may be traveling near the speed of light at very, very high energy. So when they interact with Earth and they hit, say, a zircon crystal, they may hit the zirconium and actually create krypton. So this is very useful, because if a zircon crystal is exposed to these cosmic rays, then we can actually start accumulating a measurable product, in this case krypton. So the longer the zircon is close enough to the surface to interact with those cosmic rays, we're going to get a higher and higher dose. Now obviously, if you're buried deep enough, you're not going to be interacting with cosmic rays. So this can be used as a measure of how long a zircon grain has been near the surface. So how quickly was the denudation rate, or how long was that sediment sitting near the surface within the sediment pile itself and being reworked actively. So this 78 krypton is stable, which means that we can now access deeper time records through these cosmogenic nuclides. A lot of the other ones are kind of radioactive, and so they give us a shorter period which we can go back in time. We applied this technique for the first time looking at these ancient sedimentary systems. We applied it to the southern margin, so looking at these heavy economic deposits along the southern margin of Australia through different deposits, and we were able to reconstruct the average kind of erosion rate being extremely low, kind of getting down towards some of the lowest rates we see on the world today around Antarctica and Chile, despite it being in the Eocene, when we would have expected a more humid climate and a higher rate of maybe these erosion rates. And what this is suggesting to us is we had low erosion rates, but we also had, which enabled a high accumulation of krypton, but we also had extensive reworking of the grains going on in the sedimentary pile. So it would be going stored in coastal plains and reworked onto a beach, and this sort of near surface reworking allowed also an accumulation of the cosmogenic krypton. So we could see differences between these different deposits, and we could relate particular characteristics of the deposits to that history of the grains, near surface exposure, and maybe tectonic history and duration of high stand, low stand, that sort of fluctuation. Those sorts of patterns were now actually accessible through the application and integration of this cosmogenic krypton, uranium-lead provenance dating. So it's really starting to get a much more refined look of understanding why these deposits are the way they are on the southern margin of Australia. Another thing obviously that's quite important is looking at the scalability, reproducibility and accuracy of some of our analyses, and people are becoming much more aware now of the different biases that exist, whether they're geological biases, talking about different mineral fertility, how easily different resources are eroded, kind of different selective upgrading in different facies maybe, but also kind of more critically in things that we have a bit more control over are the methodological biases and what we're doing actually to the samples that may be biasing the results we're getting out of it. And more papers coming out in terms of how we can start addressing these. So operator biases is something that a lot of people feel like quite uncomfortable about in terms of accepting the dangers of it, or putting their hand up and recognizing that it's maybe something they're doing isn't the ideal way to do it, maybe just something that they've inherited in terms of what way they have been doing. And there's often insufficient documentation in papers in terms of the approach they've taken, and therefore what the limitations of the interpretation may be based on the fact that they undertook a certain approach. And this has even come up in some of our papers where a student of ours was accused of fraud, where we were looking at basically the bias in hand-picking versus bulk mounting, and the suggestion and the demonstration that hand-picking often goes towards certain shape grains, more colourful grains, kind of better, longer aspect ratio grains, and this obviously has a significant impact in potentially the interpretation of where you're saying this sediment has come from, or the geological history of that region. And this is evidence that this is still a problem, and that we're looking at kind of 100 different papers. What proportion of sample methods are actually based on bulk mounting, which should be the preferred one, versus hand picking still being quite well represented in the literature. Now obviously hand picking can be important when you are specifically targeting a younger population, so you're trying to get a max depositional age, so maybe you will want to bias towards trying to find the youngest grain. But if you are trying to be representative of the sample, then it is important that we're aware of the limitations of the approach you've taken. And this has been demonstrated further. Some other work we've done recently looking at how the samples are kind of mounted, and how then grains are selected on that mount. So not just we've picked certain grains, but then when you're actually setting the laser points, which grains are you selecting? And these diagrams on the right look a little bit complex, but essentially what we're looking at on the y-axis is overall kind of difference from what you'd expect in a population. So if you analyze every single grain on that mount, and then you do a subpopulation, how different was that subpopulation to the entire mount? And you'd hope that would basically be as low as possible, 0. So on the right hand side of these graphs, you can see that by the time we've analysed all the grains, they are all agreeing with the full population. Now, if we only analyse the largest grains, you can see that the value stays very high for a long time. So that means that that population is very different to the total population that you've analysed. And it's the same with the smallest grains, and these are quite similar to, maybe the largest grains may be quite similar to limitations of the laser spot. You may only be going for the largest grains, but being aware of that is that you may be therefore biasing the population, because there is a link between the shape and size of zircon grains and maybe a source region. So largest grains may only be representing a single age. Now if we look at two different populations in this context, the blue being a sample of well-sorted kind of beach heavy mineral deposit versus the Swan River, which is a bit more irregular in size, these impacts are much more significant for these more kind of variable populations. And what we've demonstrated is that to be most representative and efficient in a lower number of grains ensuring reproducibility, then you want to try and select grains that are representative of the population. And one way to do that is by grain size. So ensuring that the subpopulation that you analyse on a mount is the grain size variation in that matches or is representative of the overall grain size variation of your zircons across a mount. And there are programs that will do this for you now. So this is becoming a greater awareness, and also helps us understand what sort of numbers of grains we should be analysing to get below certain thresholds of reproducibility that we'd expect within a single formation or within a single sample. This D value we're talking about here. And this is becoming clear as well in terms of larger scale studies that are in development, where 2 different heavy mineral concentrates were shared to 30 different labs in this case globally, and we've now been gathering data from those labs in terms of uranium-lead analyses. So over 12,000 analyses have come in, and documentation alongside that in terms of how were those mounts prepared. Were the grains picked? Were the spots selected? Was there imaging undertaking which influenced where the spots were placed? Or what was the strategy behind where the grains were placed? And you can see in these cumulative age distribution plots that there is quite a lot of variation within those mounts. But where there is greater variation is where we'd expect in terms of operator mediated, showing the biggest outliers. And again, essentially the message coming through this is that the least we can do to modify in terms of our processing of our sample, different separation techniques, or different selection of grains, the less humans involved, the more reproducible it is. So any kind of handling increases the chance of distortion, essentially. Another thing that's developed in recent times is looking at these big data. So rapid ablations is one way of considering big data, that we are now about 2 orders of magnitude faster in our data collection for some of these, say, uranium-lead geochronology than we were in the past. So we can now kind of go to these, we've got these global compilations of data sets. We can also start looking at a basin to craton to continental scale kind of data collection in quite a small, more manageable time frame. And we can also get representative numbers of grains analysed to pick up subtle contributions, or really get down to resolving the similarities or distinctions between samples above background noise. And we have statistical mechanisms that are much better these days of interrogating our similarities of samples. So there's no more kind of subjectivity in the eyeballing of patterns, and this can help with our approaches to maximum depositional age, resolution of minor contributions, and the likelihood of shared origins. So this sort of sediment mixing model from Sunderland Sailor is a really good example of how we can look at, okay, we have these 3 different sources, I've characterized each one of those, and we have this mixed signal. Well, what sort of proportions are we looking at from those different sources which would explain this? So these are really nice kind of examples of some of these computational techniques that will do a better job of what we were previously capable of doing. Obviously, automated mineralogy is another really important kind of advance, so and source of big data. So these automated mineral mapping using scanning electron microscopy and EDX integrated with it, whether we are looking at individual samples, it allows us to really start scaling up the quantified kind of comparison of samples. So we can look at the presence, relative abundance, and internally maybe even the mineral chemistry, to be able to see, in this case, alteration on the outside of ilmenite towards more leucoxenized grains. So important kind of environmental processes, but also understanding for these economics of deposits. And this has been utilised very nicely in terms of the Geoscience Australia and the John Data Centre kind of heavy mineral map of Australia, where over 1,000 samples were taken across the continent. 145 million mineral grains were identified, and 163 different mineral species were identified. And this has great kind of, like I mentioned before, in terms of footprints of ore systems, but also being able to link these grains specifically to a modern system and interrogate things this way. there's an equivalent map of Western Australia being developed at an even more tightly spaced grid. So we're looking at 40 kilometres by 40 kilometres grid, 180 samples, and over almost 1,500 samples expected. 180 per phase of these different maps, and you can see the grid there in terms of what they're expecting. So where did we take these heavy mineral maps of Australia? One example of some of the work we've done is looking at the well-established kind of heavy mineral ratios that people have been using for a long time in terms of understanding provenance, but also saying something about environmental influences or modifications of that sediment. So we took those sample sets that the Heavy Mineral Map of Australia released, and we looked at it in the context of modern climate, elevation, bedrock, the climate zones, weathering intensity, to start being able to understand the ratios that have a useful correlation to maybe bedrock, or which ones are tracking something like a modification from an environmental signature. And then we can better use these tools for ancient sedimentary systems. Other kind of people have been working on this in terms of, because there's now large enough data, they can use this for more meaningful mapping, modeling, and machine learning and AI integration. So this is a map from Pearson et al. This year, looking at heavy mineral hosted rare earth potential. And obviously this is something that there's a lot more to come from in this space. We can also look at non-traditional traces and characterization. So a new development recently is looking at some of this image analysis. So it's not just chemical information that can be diagnostic in some of these larger sample sets and things that people have been collecting for a long, long time and archiving just images of grains, but the mineral color, shape, the growth texture, and the external texture can tell us a lot about maybe the source region of that grain, but also in terms of what it is experienced in an environment, in the sedimentary environment. So a new program that we developed is called Analyzer. This is a web-based application that will take images of mineral mounts. It will segment the grains, identify the grain boundaries, and then start analyzing the shapes of those grains, capturing maybe information depending on which image you have in there, whether it's reflected light, transmitted light, or cathode luminescence. It can take something about the texture of the grains maybe and quantify something about the texture, but it also can correlate with any sort of analytical spots that are being placed on the grain. So it can start then linking the shape characteristics to maybe uranium-lead geochronology or trace elements. It can link it to the sample's whole rock geochemistry, and it can also start looking at comparisons between samples to say which one's similar, which one's not. Maybe it could say something about, yes, this sand is from this mine or not, or obviously in a geological context we're often looking at whether this sample matches this other sample and therefore the provenance may be shared. We've also looked at shape in terms of reconstructing something about the source rock composition, so with a sample set across Western Australia in different source regions, different ages. We looked at shape and linked it to the source region's silica, and we were able to come up with, through this machine learning algorithm, some sort of relationship. We then tested it with a subset of the data that the algorithm that was developed hadn't seen, and it seemed to come in quite nicely that there was this correlation that we could predict whole rock silica based on zircon grains. And we took that same algorithm and applied it to zircons from Greenland, and also demonstrated that even there, completely separate sample set that had never been involved in any of the training set, seemed to match up quite nicely in terms of the inferences. Now obviously this is working at a population scale because there is variation within individual samples. But obviously we can also look at using grain shape for more simplistically saying where have these zircon come from. And this can be useful where maybe uranium-lead ages or hafnium isotope data or trace elements are non-unique and don't tell us which specific source region something's come from. Shape can be another kind of modifier, another fingerprint that we can use to say something about the source. We've taken a lot of these tools and we have put them together into an online platform to try and help people understand some of the different techniques that are out there, what different minerals can be used, and this is particularly kind of focused towards people in industry about maybe some of the different techniques that may be available to help them understand different aspects. So whether it's source characterization, transport, or depositional constraints, or maybe which specific mineral they have and what we might be able to do with it. Thank you very much for your time. If anyone has any questions, please let me know.